In organic chemistry, we need to be able to interpret different representations of organic molecules. At the simplest level, the molecular formula tells us the atoms that make up the molecule, but such information is not helpful when we need the structure of the molecule. Simple molecules such as methane or ethane are easy to represent with line-bonded structures, but more complicated molecules are cumbersome to draw. For example, the line-bonded structure for testosterone looks like this. There are two primary ways that we simplify structures: condensed structures and skeletal structures. Condensed structures eliminate most or all of the bonding lines and show carbon-hydrogen groups. Consider the following molecule. To generate the condensed structure, first group all of the hydrogens with their respective carbons. For example, this carbon has 3 hydrogens bonded to it, so we write CH3. It is bonded to a carbon with 2 hydrogens bonded to it, so we write next to that CH2. Now, to generate the condensed structure, we eliminate the lines and we put branches in parentheses like this. Notice that there are 2 CH3 groups bonded at the end of the carbon chain, so we write that with a subscript 2. Skeletal structures are simpler still. In a skeletal structure, we do not write carbon atoms or hydrogens bonded to carbon atoms unless those atoms need emphasis. Instead, we draw all of the bonds where carbon atoms are at the intersections and ends of the bonds. We do write all other atoms and hydrogens bonded to atoms other than carbon. Let's work through 2 examples. The line-bonded structure for benzoic acid looks like this. To draw the skeletal structure, draw a hexagon that includes the 6 ring carbons, add 3 double bonds, then add a bond for the non-ring carbon, which has an oxygen double bonded to it and an OH group bonded to it. As a second example, this is the skeletal structure for vanillin, the primary component in vanilla extract. What is its chemical formula? First, let's count all of the carbon atoms, 6 in the ring and 2 outside the ring for a total of 8. Now let's count the hydrogen atoms. 3 of the ring carbons have 4 bonds, so those carbons have no implied hydrogens. 3 of the ring carbons have only 3 bonds, so those carbons have 1 hydrogen each. The aldehyde carbon here has only 3 bonds, so there is 1 hydrogen there, and the terminal carbon has 1 bond, so it has 3 hydrogens, and there is 1 hydrogen bonded to an oxygen for a total of 8 hydrogens. Finally, there are 3 oxygen atoms, so the formula is C8H8O3.